Welcome back to the last 10 days of the 100 Days of Logic. Ooh, we're getting close to the end with day number 98. Today we will be continuing with looking at predicate calculus and looking at something that's actually really complicated. It's known as modal logic. Now, like I said, modal logic is pretty complicated. We're not going to be getting into all of modal logic in one video. We're going to be trying to cover the basics, give you some understanding of the different versions of modal logic and some of the disagreements that exist, and then trying to give you a little bit of a sense of how to use modal logic in kind of a propositional logic form. The most important things you need to know about modal logic is there are two new symbols. We're adding the box, which is going to represent necessity, or it is necessary that, and the diamond, which is going to represent possibility, or it is possible that. Let's take a look. So, before we get going, there's an important distinction we have to make between modal logic and modal logics. Modal logics is a family of logics that includes modal logic, but also deontic, temporal, and doxastic logic. That is not what we're going to be looking into today. We're only looking into the modal logic part of the larger family of modal logics. There's also a distinction we need to make between modal logic and modality. Modality is kind of the contents of modal logic. Modal logic is the rules. So modality is what we mean by something being necessary or possible. These are things like modal realism, modal fictionalism, and modal combinatorialism. These different versions of modality or understandings of modality are something to do much more with metaphysics than logic, and hopefully in another series I will take a look at the proponents of all these different theories. They're actually pretty interesting, but not in this video. What we will be looking at is modal logic. Modal logic is what follows logically from something being necessary or possible. Different versions of modal logic look like K, S4, and S5. If you've heard anything about modal logic, you've probably heard about S4 and S5. Don't worry, we're going to be talking about that disagreement here in this video. Now, the first modal logic system that we're going to be looking at is system K. This was named K for Saul Kripke. It is the most basic and most simplistic system of logic. It has three main components. The necessitation rule. If A is an axiom of K, then it's necessary that A is as well. Basically saying that the laws of logic are necessary, or our axioms are necessary and true in all possible worlds. The distribution axiom. This one's a little tough to kind of see the implications of just looking at it, but there's a lot buried in here and a lot of kind of deep ideas. The basic idea is that if an implication statement is necessary, then the two participants of that implication statement are going to be necessary when put into another implication statement. Or we can just distribute that necessity, that box, over A and B. So the statement reads as follows. It's necessary that A implies B implies that it's necessary that A implies it's necessary that B. We also have the definition of possibility. Possibility is just going to be defined in terms of necessity. So in other words, whenever we saw possible, we could just replace it with it's not the case that it's necessary, that it's not the case that A. This should look similar or familiar, if you remember back a couple days ago, to our change of quantifier rule for predicate calculus and for the universal and existential quantifiers. This is the same kind of thing. And in fact, there's a lot of similarities that you should see between necessity and the universal quantifier and between possibility and the existential quantifier. They're not perfectly identical by any means, but there are a great deal of similarities between them. This is a very simplistic system, system K. It's not able to perform many operations, but one thing that K is not really controversial. No one really disagrees with us having or using K as a system, and in fact, it's the basis for pretty much every other modal logic system. The next one we'll look at is system D. System D is going to be everything that we had in System K with the addition of Axiom D. Axiom D is going to be that if A is necessary, then A is possible. Whatever is necessary is possible. This is going to be the weakest system that we're going to really look at, and it's often used with deontic logic instead of modal logic. Hopefully, one day I'll do a series of videos on deontic and temporal logics, but for now, we'll just leave them. Next up, System T. System T, this is also known as System M, so either one, they're actually referring to the same system. System T is going to be System K with the addition of Axiom M. What is Axiom M? Axiom M is it's necessary that A implies that A. Whatever's necessary is just going to be the case. This is a stronger version of D, and it's more commonly used with modal logic. It's important to note that contained within this axiom is D. We don't need D anymore. That's why we can just directly add M to K, because D is actually going to be contained within M. Why? Because there's a corollary to M, something that just follows directly from M, which is that A implies that it's possible that A. And it should be pretty clear that we could then conjoin these two with hypothetical syllogism and just get D. As we can derive D from Axiom M and System K, there's no need for us to have that axiom anymore in System T. Here is where the kind of non-controversial part of it stops, and we move on to some more controversial pieces of these systems. We're going to now be talking about System S4. This is going to be System T with the addition of Axiom 4. Axiom 4 is going to look like this. It's necessary that A implies that it's necessary that it's necessary that A. Basically, this is going to be a kind of way to either simplify or complicate long strings of necessity and possibility. Whatever is necessary is going to be necessarily necessary. That there's nothing more that we mean by adding a bunch of boxes in front of something or adding a bunch of necessaries other than just that it is necessary. To recap, System K is just going to be System K. System T is M and K. And System S4, System 4, is M, K, and Axiom 4. As with the other systems, there's a corollary to S4, which is going to be it's possible that A implies that it's possible that A. Note that Axiom 4 and its corollary, along with M, allow us to reduce any homogeneous line of either boxes or diamonds, as long as they're only boxes or only diamonds, down to just one of whatever that is. Or extend a single box or a single diamond to a long line of those. The key is they have to be the same. That's where things get changed up for our next system, S5. System S5 is going to be System T and Axiom 5. Similar to how Axiom M was stronger than D, was a stronger version of D, and so we didn't have to restate D. Axiom 5 is a stronger version of Axiom 4, so we don't need to restate 4 here. Axiom 5 looks like this. It's possible that A implies that it's necessary that it's possible that A. Whatever is possible is necessarily possible. As I noted before, we're not adding both 4 and 5 to K and M. We're just adding 5 because we can actually get 4 from Axiom 5. And there's going to be a corollary to S5, to Axiom 5, which is going to be it's possible that it's necessary that A implies that it's necessary that A. That corollary is where a lot of people are going to start to have a little bit of trouble with S5. Basically, the point of S5 is you can reduce now long strains of different versions of possible, necessary, possible, necessary, possible, necessary, down to whatever the last one in that line is. Finally, the other system we're going to take a look at that will help with our discussion of S4 and S5 is going to be System B. System B is going to be System T and Axiom B. The reason it's important is S5 can be formulated either by adding 5 or B and 4 to T. Basically, B is the difference between system 4 and system 5. Well, what is B? B is going to be the axiom that A implies that it's necessary, that it's possible, that A. Whatever is the case is necessarily possible. The corollary to B is going to be something, once again, it's another one of those strange corollaries that are going to give people trouble, which is it's possible that it's necessary that A implies that it is in fact the case that A. We're going to look a little bit more in depth into these confusing corollaries in a second. But first, as I've stated before, kind of in passing, I want to state clearly now. S4 and S5 are systems that there's a big debate over which system we should use. The reason this debate exists is because S5 is the system of logic that is used to do the modal ontological argument, while in S4 or any of the other systems, that argument is not going to succeed. You need S5 in order for that argument to work. So, people who are proponents of the modal ontological argument, of course, want to convince you that we should use S5, whereas opponents of the modal ontological argument are going to say that we shouldn't want to use it. The important point here is that the difference between S4 and S5 is going to be principle B. Yes, it can be distinguished as whether you're adding 4 or whether you're adding 5 to K and M, but remember, 4 is basically contained in 5, and 4 and B are equivalent to 5. So the key difference here is whether or not we should add B to our system. Now, if you want some other reasons to deny the modal ontological argument, I have a whole series of videos debunking the modal ontological argument 6 ways from Sunday, where I offer 66 different objections to that argument without once mentioning S4 or S5. Because I want to make it clear that there's a lot of other reasons to object to or be skeptical of that argument, other than just kind of some basic distinction of which kind of logic we should use. That said, if those objections weren't convincing, take a look at this kind of explanation that exists in the Stanford Encyclopedia of Philosophy, which explains why S5 and B aren't terribly intuitive. So, axiom B is A implies that it's necessary that it's possible that A. Whatever is the case is necessarily possible. This seems pretty intuitive on the face of it. The corollary to B, however, is very unintuitive. That's, it's possible that it's necessary that A, therefore A. If something is possible that it's necessary, if some necessary thing is possible, then that necessary thing exists. That seems to be something that's really strange and not something that we would normally accept. That is, whatever is possible necessarily is the case. The Stanford Encyclopedia of Philosophy offers the following explanation of why this might be a problem. So, we have axiom B, but axiom B is a little ambiguous, or at least the statement, whatever is the case is necessarily possible, is ambiguous between two logical interpretations, either axiom B or something that's already in our logic once we have M and K, which is, it's necessary that A implies it's possible that A. This statement, necessarily, whatever is the case is possible, already exists as a consequence of M and K in our logical systems. However, if you interpret the statement as axiom B, you'll end up with all these weird consequences, whereas if you interpret it as this consequence, things will seem fairly normal, and you'll have the normal logical system that you already expected. So, if you want to interpret the statement as the statement below, you won't end up with all of the weird corollaries, nor will you end up with the modal ontological argument. But if you want to interpret it as the statement above, I would say that you're being disingenuous really to kind of the understanding that most people have of what that statement means. That is, whatever the case is necessarily possible. We can also see that this problem is going to appear for axiom 5 as well. This is not just going to be a problem for B, though that is an important part of system 5. Axiom 5 is, it's possible that A implies that it's necessary that it's possible that A. Whatever is possible is necessarily possible. The corollary to 5, once again, is going to be the kind of disconcerting, worrying thing. And that's going to be, it's possible that it's necessary that A implies that it's necessary that A. Basically, whatever is possibly necessary is just necessary. Once again, the corollary is a little worrying, and we're going to find the same kind of problem or confusion. The corollary is worrying because it seems that if it's even possible in some way that something is necessary, then that thing in fact is necessary, which just seems like a little weird. So perhaps then what we mean when we say Axiom 5 is actually something that's already a consequence of K. That it's necessary that it's possible that A implies that it's possible that A, which is very concrete and makes a lot of sense. So when we're saying necessarily whatever is possible, that's something that seems to be a lot more sensical and more clear than Axiom 5, which is whatever is possible has to be necessarily possible, which is saying a very different thing than necessarily whatever is possible is possible. This corollary, of course, or rather this consequence of K, would have none of the same problems or confusing corollaries that Axiom 5 does. As I've said, it already follows from our logical system. So, the rules of inference that we can get out of all of these different systems, let's take a look. There's the necessitation rule. That was one of the first things we learned about. That's A implies it's necessary that A can be abbreviated with NR, and this is only going to be allowed if A is an axiom of the system. It's been inferred solely from the laws of logic. You don't want to be using this rule willy-nilly. It's the kind of thing that only works for things that are already axioms or already rules of whatever system you're using. We have the change of modal quantifier. We're going to do CMQ to represent that. This is going to be extremely similar to normal change of quantifier, but it's going to be with our modal operators, of course. This is just one way to represent it. Of course, there's the other 3 ways to represent it as well. If you don't understand what I'm talking about, check out my previous video on change of quantifier, just for general, normal, good old-fashioned predicate calculus, and replace existential and universal with possible and necessary. And you'll get the gist. The distribution axiom, you've already seen one version of this. I'm going to add 2 more that the Stanford Encyclopedia of Philosophy gives us as other versions of the distribution axiom. We have, it's necessary that A implies B implies that it's necessary that A implies it's necessary that B. We also have one for conjunction. Note that with implication, we're going one direction, from the necessary box being on the outside to it being on the inside. With conjunction, we can go both ways. It's a rule of replacement. You can either go from, it's necessary that A and B, therefore, it's necessary that A and it's necessary that B. Or you can go from, it's necessary that A and it's necessary that B, back to, it's necessary that A and B. The final version of this, the disjunction, is going to be a little bit different as well. It's going to be going the other way from implication. It goes from, it's necessary that A, or it's necessary that B, implies that it's necessary that A or B, but it doesn't go backwards the other way. I'm going to just represent that with mdist. We already have a dist, D-I-S-T, for distribution. This is going to be modal distribution, mdist. Makes sense to me. We also have our good old-fashioned axiom M, which is pretty simply, it's necessary that A implies that A, and the corollary, A implies it's possible that A. We'll abbreviate that with an M, pretty simply. Axiom 4, it's necessary that A implies that it's necessary that it's necessary that A, and the corollary, it's possible that A implies it's possible that A. Abbreviate that with S4. These are the basic rules of inference that will pretty non-controversially be used in modal logic. I'll also show you S5 and B and how they might be used, but you generally won't see me using them in my logic. And in fact, for the most part, the only pieces of this modal logic you'll really see being used are going to be the change of modal quantifier, the distribution axiom, and axiom M. The other ones are either superfluous or generally not what we're going to be talking about because we're not focusing on kind of proving the laws of logic, which is how you would be using the necessitation rule. Axiom 5 is going to be, it's possible that A implies that it's necessary that it's possible that A, and it's possible that it's necessary that A implies that it's necessary that A. S5 would be how it would be abbreviated, and A implies it's necessary that it's possible that A, for axiom B, and the corollary to axiom B, it's possible that it's necessary that A implies A. It's going to be B. Those are the general rules of inference you can get from modal logic. There are other ones out there. Like I said, this is going to be a basic introduction for modal logic, so we're not going to cover every single rule of inference out there for modal logic. Hopefully in future videos, we'll look more into kind of the details and an understanding of where modal logic comes from, some other logics in the modal logic family. But for now, we're going to finish up with a logic problem using modal logic. This is going to be, we are going to actually try to prove an axiom of modal logic. We are going to prove that it's possible that A implies that it's possible that B implies it's possible that A implies B. It's kind of an interesting switch around of the distribution axiom with possibility instead of necessity. Well, we don't have any premises for this, so we have to either stipulate some axioms or do a conditional or an indirect proof. Personally, I like doing indirect proof in these cases. So, I'm going to start off with premise 1, assumed indirect proof. It's not the case that my whole conclusion. I'll stop here. If you want to pause the video, you should have paused it a second ago. You can pause it now as well. I haven't given away that much. And try this on your own. I would warn you, however, that we are going to be working with rules that I just taught you, and I haven't taught you everything, so you'll be perfect at them. But I would encourage you, if you're brave and courageous, to give it a try on your own and see if you can do this on your own. Most of the rules and most of the laws that we'll be using are things that we have already learned. There's just going to be a few new additions to account for possibility and necessity. With that out of the way, let's continue with the proof. So, I did an assumed indirect proof, so I want to draw my line going down. Now, the first thing I want to do is somehow be able to get that negation in from the outside, because it's kind of holding things back. But I don't have anything that lets me get rid of that negation when I have an implication. So I need to change my implication to a disjunction. I can do that, premise 1, implication. Switch things around, and I'm going to negate the first part of that implication to keep it valid. Then, oh lovely, we can bump that little negation sign that was out front, kind of binding everything up inside with De Morgan's law, and get it's not the case that it's not the case that it's possible that A implies that it's possible that B, and it's not the case that it's possible that A implies B. Premise 2, De Morgan's law. This is a great result for us because we now have a lovely conjunction that we can simplify down and play with. But first, we're going to want to do some double negation. Premise 3, we'll get rid of those two little negations out front of the first part of our conjunction. Then we'll simplify it down to it's possible that A implies that it's possible that B, premise 4 simplification, and it's not the case that it's possible that A implies B, premise 4 simplification. Next up, what we're going to do, because we can't work with that negation outside of the possibility, we can't move that into, play around with it with the A and B, we're going to change our modal quantifier. Premise 6, change a modal quantifier, and we'll switch this to it's necessary that it's not the case that A implies B. Then we'll do implication. Once again, we're doing the same process we just did with the first premise up there. We're going to switch the implication and then do a De Morgan's law to get rid of that negation outside our parentheses. And then what we're going to do is we are going to distribute our little box. We're going to distribute our necessary box. Remember that one of our rules for modal distribution was that we could distribute when we had a conjunction. We'll bump the necessary box into both of our two parts of the statement. And then we will simplify out to get it's necessary that it's not the case, that A. We finally need to do some double negation on that because that's just way too much to say. To get it's just necessary that A. Premise 11, double negation. From that we will conclude A. Premise 12, M, or axiom M. And then, once again using axiom M, we will conclude it's possible that A. Premise 13. Why did we want to get it's possible that A? Well, way back up in premise 5, when we simplified down premise 4, we had an implication, and we want to use good old-fashioned modus ponens, as always, to get it's possible that B from 514 modus ponens. Now that we have it's possible that B, we're working towards a contradiction somewhere in here. So now we have it's possible that B, we need to get it's not possible that B. Well, how can we do that? Well, we had something that was pretty close to that in premise 10, which we can simplify down to it's necessary that it's not the case that B. Premise 10 simplification. And then, if we use our change of modal quantifier rule, we'll end up with it's not the case that it's possible that B. We can join those two, and we get it's not the case that it's possible B, and it is possible that B. Premise 15, premise 17, conjunction, that is a contradiction, so we are allowed to conclude the opposite of our original assumption, which is going to be, it's possible that A implies it's possible that B implies it's possible that A implies B. Premise 1 through 18, indirect proof. Wow, if you were able to do that on your own, I'm very, very impressed. That's awesome. Once again, with all of modal logic, it's not like a lot of other kinds of logic because there are people who are going to disagree about certain pieces of it, but for the most part, everything that was done here is fairly non-controversial. That was modal logic. Next up, we are going to be doing some final logic problems and the answers to those problems, and then finally a special surprise for our 100th video. Watch a new video every single day for 100 days here at Carneades.org. And stay skeptical, everybody.